It is my pleasure to introduce Alan Bourgoyne. He is Director of Product Marketing here at NVIDIA, and he's going to be talking to us about Project Digits. A warm round of applause for Alan.
Thank you, Seppi, and that 20 IU is on the way. I'll give it to you after the show. So I know it's Thursday afternoon, it's late. How many people are ready for a drink? I am. I could be ready for a couple drinks. So hopefully we'll have an entertaining show today. Take a look up. So DGX Spark, from Project Digits to your personal AI supercomputer. At CES, Jensen did a keynote back in January, and he announced Project Digits. Grace Blackwell Superchip AI supercomputer for your desk. 1,000 AI TOPS, 128 gigs of memory, runs our AI stack, very tiny. You can see the picture there, fits on your desktop. Project Digits was an homage to a system we released back in 2015, the Digits box. It was our first AI training box. It was a workstation with 4 GPUs in it. The big old software stack on it was the first box really dedicated to training. A year after that, we released our first DGX system. So Digits was kind of the precursor to DGX, and so the name for Digits was that homage. How many people saw the keynote? How many of you saw it at the SAP Center? All right, if you didn't see it at the SAP Center, you missed something. There was a glitch in the stream, and I'm gonna show you what you missed.
Of software engineers in the future, there are 30 million of them around the world. 100% of them are going to be AI assisted. I'm certain of that. 100% of NVIDIA software engineers will be AI assisted by the end of this year. And so AI agents will be everywhere. How they run, what enterprises run, and how we run it will be fundamentally different. And so we need a new line of computers. And this is what started it all. This is the NVIDIA DGX 1. 20 CPU cores. 128 gigabytes of GPU memory, 1 petaflops of computation, $150,000, 3,500 watts. Let me now introduce you to the new DGX. This is NVIDIA's new DGX, and we call it DGX Spark. DGX Spark. Now, you'll be surprised. 20 CPU cores. We partnered with MediaTek to build this for us. They did a fantastic job. It's been a great joy working with Rick Tsai and the MediaTek team. I really appreciate their partnership. Built us a chip-to-chip NVLink CPU to GPU. And now the GPU has 128 gigabytes. And this is fun. 1 petaflops. So this is like the original DGX1 with PIM particles. You would have thought that that's a joke that would land at GTC. Okay, well, here's 30 million, there are 30 million software engineers in the world, and it's, 10, 20 million data scientists. And this is clearly the gear of choice. Thank you, Jenny. Look at this. In every bag, this is what you should find. Right? This is the development platform of every software engineer in the world. If you have a family member, spouse, somebody you care about who's a software engineer or AI researcher or just data scientist, and you would like to give them, you know what, the perfect Christmas present. Tell me this isn't what they want, huh? And so, ladies and gentlemen, today, we'll let you, we will reserve the first DGX Sparks for the attendees of GTC, so go reserve yours. You already have one of these, so now you just gotta get one of these.
And so you can imagine how excited we were. All the people have been spending months and months working on this project. And of course, when our moment comes up to shine, the stream glitches and you don't see that part. So it's, what can you say? But Jensen, when he started that talk, he said he doesn't have a script, no script, and he's not lying. But the one part he wasn't lying about is you can reserve digits today. You can actually go online and reserve those. We're going to send you a notice next week to remind you, but you can go online and reserve yourself a system today. You know, it is a new class of computers, right? It's designed from the ground up to run software. You saw the comparison. Those numbers weren't by accident what you saw from that DGX1 to what we have today, the memory, the flops, right? It's designed for AI from the ground up. Runs our full AI accelerated software stack. Everything runs there. It's going to be available from our OEM partners, Asus, Dell, HP, Lenovo. You can actually go to the show, look at the Asus, the Dell, the HP boxes. You can see their prototype. It's on sale on the NVIDIA marketplace right now, and I just happen to have one of the prototype systems right here for us to take a look at. Maybe somebody will get a selfie after, but this, I feel like the Lion King. There should be real dramatic music playing right now. Do we have to, can we cue that? Not even, I guess only Keynote gets that kind of advice, but thank you. There you go, there's one right there. And so why do we build these things? You saw a lot of this in the Keynote, right? AI is evolving rapidly. AI agents, kind of the big thing now. We want AI to help us do things, right? We want AI to collaborate with other AIs to do things for us, right? Healthcare agent, it should be able to help the doctor diagnose things, pick out medicines, right? It's more than one model doing these things. I would love it if for travel, you're out on, most of us are on travel this week, you have to extend a day. What do you have to do? You got to call the hotel, you got to call the rental car place, got to call the airline. It'd be great if agents just did that for you, right? And helped you make those decisions and make those things. So AI agents are getting very popular and businesses are using them. Why? Because they're useful. They help people do their jobs more efficiently and more effectively instead of having just point AIs. The rise of reasoning AI. Jensen talked a lot about this, all of those new models where the AIs, not only do they go through the model once, they go through it multiple times. They try to find the best answer, right? That's the DeepSeek model. That's the reasoning models. So, and a lot of times you can see them think, right? If you use Perplexity or some of the new models, you can actually see it thinking, right? And it's generating a lot more tokens than before. And so when Jensen talked about the scaling laws, that axis on the bottom is very important. The more intelligent I make the model, the more it can reason, the more compute I need, right? So those scaling laws are out there. And so when we're making these kinds of systems, we need more powerful desktop systems. If you look at our local systems today, we run a lot of our AI workloads. Like, how many of you do your AI workloads on your desk? You can do it on your laptop, or you can do it on your PC. But sometimes things don't work there, right? Maybe the model's too big, the workload's too big. I'm trying to make an agent. I want to run 3 or 4 models at the same time. A little bit too much for my laptop, so I have to go out to the cloud. Or maybe I want to use some software that doesn't run well, or maybe it's not actually ported to my device. And so a lot of times you have to go off device. And so that's why we created this new class of AI computers, right? We want to have systems that are powerful enough to help you offload desk and literally create your own personal cloud, right? Your own personal data center on your desk. And by having these systems like DGX Spark and DGX Station, our full accelerated software stack, all of your favorite tools out there like PyTorch and Jupyter Notebook, all of that stuff just runs, right? And so your environment just comes over, and now you've got your own personal cloud. And if we look at the software stack, now, before anybody cuts me to shreds, this is my marketing version of the software stack, and I know all you engineers, it's not 100%, but I try to fit it on one slide so we can look at it a little closer together. But down at the hardware, that's our GB10 Superchip, right? It's got the CPU, the GPU, encode and decode engines. It's got our optical flow accelerator in there. It's got our CX ConnectX chip in there for networking. We've got our DGX OS. This system runs the same OS that our DGXs run in the data center. Same exact software. All of that's there, all the containers, everything we do to accelerate that kernel, and of course, our CUDA libraries. That's where a lot of the magic happens, right? That's how we get to the hardware, provide you the libraries and toolkits you need to accelerate all of the higher level frameworks, all of your favorite tools that are out in the market today. And of course, the great tools that we provide, things like NIMS, AI blueprints, AI workbench. All of those are all supported thanks to the beauty of our software stack that just runs everywhere. And so this was kind of the design goal. Take that software stack and leverage it. And look at that. I do have production values. I made the arrows move. You can write it once and move it wherever you want to go. You can work on your Spark. You can move to DGX. You can move to the cloud. Basically, any accelerated infrastructure you've got, you write it once. And it's ARM-based, so all the ARM code's there. It runs. We develop. We work through all the tools for you. So if you're working on a DGX, we all know how hard it is to get access on that system and get access to that data center or cloud, right? So it's great. You can prototype, you can work out all the kinks, test, and that way when you finally get your slice of time in the data center, you're a lot more confident. You don't have to experiment quite so much by using that Spark system on your desk. And it truly is your personal cloud, right? You can take all these workloads, you run them on your Spark, you could have your systems connect to it. It's going to be really easy to install. Our out-of-the-box plan is to let you install it basically like you would put a thermostat in your house, right? You're going to hit its network. You're going to give the information, what's the network I'm on. It has wireless network. It has wired network. You're going to give that information. It's going to restart itself, and now you've got a network-connected compute device. Really easy, simple. It's a full computer. It's got ports. You can plug a mouse and keyboard into it. It's got Bluetooth. You can wirelessly connect your mouse and keyboard. It's got an HDMI port on the back. You can plug a display into it. So you can use it as a standalone device if you'd like to, computer. But the beauty of it is either way, you've got your own personal cloud that you can send all of your bigger jobs to. I mentioned the ConnectX chip in there, and that's a really important feature of this box. It lets you connect two of these systems together to basically form a little cluster. So you've effectively doubled the memory, doubled your compute performance. And so have it on network, have it your desktop system. Now you've got an even more powerful system. Work with models up to over 400 billion parameters with the combined memory from those two systems. So I think I showed you the back of that thing. You can see those ports. They're the big giant ports. If you go on the system in the back, you'll see where those ConnectX cables connect to. They're kind of big cables. They plug into the back, and that's what gives you much higher performance than using on the network. So we'll allow you to form your own little mini cluster on your desktop if that's what you want to do. So as far as workloads, it really is for AI developers. Model prototyping, development, do your development work there. Maybe you want to develop AI augmented applications. You want to create AI chatbots. You want to create all the agents that we talked about earlier. Maybe use some of our blueprints to create those. Fine-tuning, you could fine-tune a model up to 70B on a single one of these Sparks. And we're going to show a demo in a little bit. We actually did a little of that up front to do some fine-tuning. We'll show an example. Inference, great for inference. If you want to test out a model, you've done a little work. You want to see how fine-tuned it, does it do what I want it to do? Maybe you want your own Copilot. Maybe you want to train it with your own code base, put it on your desk, and now you've got your own personal code Copilot there, right? The data's safe, secure, it never had to leave the building. I know companies would get very upset if you borrowed some cloud time and sent all your source code up there and trained a model on it, right? So the data stays there, it's local, it doesn't have to go anywhere. You saw Jensen mention data science. Our full stack runs there. Our accelerated rapids, our QDF libraries, everything is there. We also run all of our other libraries. So you can run Isaac, if you want to train robots, all of computer vision, the VLM models, all of it runs. So we're going to try to install as much of this on the system as we can. We want to make the download palatable, so we can't put everything there. There's always that trade-off. How long do you want to wait for an update to run versus how much we put on there? But the good news, everything's there. It's all free. You can join a developer's program. You can sign up for NGC. You can download everything there and try it out on your own. But a unique thing about Spark is that if you look at all of our Grace Blackwell solutions today in the data center, they have Blackwell GPUs, Grace CPUs, but those Blackwell GPUs are really maximized for compute. So people don't care if, like, things like RT cores for ray tracing, right? A couple of other things we include in there that are for graphics. They're actually there. You've got a full Blackwell GPU in a Spark. So it's got the RT cores, the Tensor cores, CUDA cores. So if you like, you can visualize on it as well. And a lot of times data scientists will want to visualize on it. It's good for compute. Maybe you want to do some simulation there. A lot of these simulations now done in molecular biology and in earth sciences using AI to actually create those simulations and run those. This box can be used to help develop those applications, and you can test it out right there. You can visualize it. It has the code there. We're trying to bring up a few applications in the lab. We brought up a protein folding model that uses a couple AI models, and we actually were able to look at it and look at using Parabricks, look at the model, the protein folding model. So people are going to use it for that. There's a lot of interest in using it for visualization as part of the workflow. A lot of people ask, how does it compare? How does it stack up to PCs and workstations? So there's a lot of words on this chart. I'll show you one in a minute with arrows that's probably a little easier to grok. But you can see across the top line, we mentioned that Spark got about 1,000 tops. Nothing like box water in the afternoon. It's really good. We've got about 3,300 tops on our highest end PC GPUs now. Workstations are up to about 4,000 tops. We just introduced our RTX Pro 6000 high-end GPU with 96 gigs of memory, very powerful GPU. And of course, data center is just variable. You can scale that out to whatever you want it to be. But if you look at the memory footprint, out of 128, you've got maybe 100 gigs plus or minus to be able to work with on Spark after you take out some room for the OS. 32 on the PC, 96 on the Pro. The data center GPUs can go up to 141, but they've got NVLink, and they can scale out to just look like ridiculously large single GPU instances. And if you look at what kind of model sizes you can run, about a 200 billion parameter model on Spark, only 64 on PC on a single GPU. They get a little higher, 198 on a workstation, but that cost of that GPU is probably way more than the Spark system costs. So if you've already got a laptop, whether you want to invest in that or not. And then multi-GPU, I'm not really sure anybody can get 4 of the 600 watt Pro card or the 500 plus watt cards. So those are probably more like 2. So by stacking 2 of those together, you can get a lot more performance. So when people ask me which one should I buy, if it fits in GPU memory on the discrete cards, probably going to be faster, right? You got more raw computing performance there. But if your challenge is that it just doesn't fit on my system, right? It's too big, too many models, the software stack's not there, then the Spark is going to be the way to go. So kind of a good rule of thumb. And if just to kind of look at this a little more visually, you can see how this fits on a PC, about a 51 billion parameter. This is all FP4. I threw out about 20% memory overhead for overhead when you're running the model, which is probably par for the course. You use a better optimizer, maybe you can squeak a little bit of that back. About 153 on a workstation, one of the new GPUs. 200 for Spark, 405 if you stack 2 of them. If you can manage to get 4 of those GPUs in there for a workstation, you can probably get a little bigger than that. And of course, DGX Station, we're still trying to pull that one together, but they're going to be very large. So DGX Station is going to be that gap between desktop and data center. So it's really set up for very large, very demanding workflows. More than likely, that might even be a shared compute resource with a couple of engineers since it's so powerful. But different play, but it gives you an idea of how all these lay out. And so with that, I wanted to take a look at a demo. We wanted to bring a system here. Just not really ready for that yet. We're very early in. We've got some development boards in-house. Networking's not great in the building. I've noticed some of the videos I'm playing are kind of laggy. We might notice some of that here. But we wanted to try to fine-tune a model. And so we've got a few videos here. The time frame on the tuning is actually compressed. It took, maybe 5-ish hours or so to tune, and I don't think everybody wants to hang around for that long to watch it tune. So we'll compress that back in part, but I think we want to step through and just show you what's going on the box. So First, we're going to take it and we're going to fine tune. We're going to take a DeepSeek R1 distilled Quinn 32B model. And we're going to use a data set we created, NVIDIA source code. It consists of 500 question and answer pairs, right? So that's our goal. We want to test this, and then we're going to ask it some questions, try to see if it can help us write some code. And so first, we're gonna set up our model. So here's the model. You can see it up there. You can see the code base, right? The NVIDIA code. We're going to do 4-bit. We're using QLoRa to help us fine tune this. And we've got data. We created that data set using Hugging Face as TRL to help us create that. And so that's our goal. We're going to try to fine tune this model on our DGX Spark. And so now we've got that set up. Let's take a look at our model. So there's a model right there. We're setting up our code. We're going to run it. You can see the NF4, so we're going to go FP4 in this. And making a model that can give us good performance there. You can see all the other parameters there, setting up for attention. And here's our data prep. We're going to walk through here. Some of my videos are not playing here, but I'm going to back up one. See if I can play some of these. Anyway, the clicker doesn't seem to like them. Of course, the monitors, you expect them to go right to left, but that's not always the case. Okay, so we'll go through, I'll drive it from here. So here we go, we'll set up the model, we saw that. And then we've got our data set we're gonna set up here. I'll let these stop at paces. You can see where we're setting things up. You can see where we're set up a prompt. So we want to do question and answer pairs. You can see the part that's coded out in red. So we can set up how we want to train the model. And so now that we've got our data set up ready to go, it seems to want to get stuck on the same slide over and over again. So I'm going to try to see if I can advance it manually. There we go. And so now we're ready to start the training. And so we've got a notebook set up, and you'll see it'll go to the training here. And we're going to open up a tensor board so we can watch what's going on in a minute. You can see getting everything going. There's our tensor board. We're going to bring that up and set that up to run. And then we'll stop it right before open. Kind of jumped right past that. Let's see if I can get it to stop there. All right, here's our tensor board. So here's what we're going to watch. Of course, we're going to watch our training epoch, all the data going through that for that epoch. We're going to watch our gradient normals, make sure we're not too high, too low, right? We want to be kind of in the middle. If it's skewing too far one way or the other, we're not getting good training out of that. Our learning rate, we want to see that kind of go up quickly and then start to peter on down. So hopefully we're training our model and it's learned all it can. Training loss, we want to make sure that the actual data is actually fitting, right? We want to make sure that our model is being trained and we're not just randomly changing weights here and there for no good reason at all. And then finally, look at our token accuracy. We want to check how well is the model answering the questions during the testing, right? So we should start to see that converge out and getting good response rates there. So now we're going to just let it roll. And again, this is compressed from a few hours worth of testing down to about a minute worth of video when it runs, so that we don't sit here all day and we can go get some drinks. You can see it's running now, and you can see all those arrows were kind of up high. You'll see our training is starting to work. The learning rate is starting to kind of come down on that middle one on the next. You can see it's kind of learning what it's supposed to do. Our training loss is going down. We're getting good responses. And our token accuracy is going up, right? The one on the bottom there. We're getting better and better as we go. And now we're kind of done with it, and that was kind of fast, but I pulled it so we can actually see kind of what happened at the end. We can look at our chart. You can see the one up on the far top, I guess it's your left. That's just our running through our epochs, right? So we're going to run through, that's going to increase. Our training gradient did kind of want to do, you saw it was kind of up high. We're doing lots of changing of the weights, but then it kind of came back down to more normalized, so that's good. If we would have stayed up high, that would have been something we'd be concerned about in our training when I wanted to look at it. Our learning rate, of course, it went up. We saw a nice, good curve. We taught it a lot. And then as it started to go through the data set, it started to do much better, and it kind of knew what it needed to learn. Our training loss, we had a lot of misses compared to what we asked it to what we wanted, but you can see it kind of converged. And then finally, our token accuracy was pretty good. It kind of went up, a little dip at the end, but that was good. We were getting good answers. The model was doing what we were asking it to do. And so now the only thing left to do is to try it and see what it does. And so here, I'm going to try to pause some things on this video so we can see what's going on a little bit. First, you can see the question, right? You said, can you help me write a PyTorch training loop using Transformer Engine Library with FP8 precision? The loop should include model initialization, loss computation, and optimizer setup. A minimal working example would be ideal. All right, so this is something you might do if you had a code copilot on your desk. Right? You'd ask it to help you do some code, right? So that you can go on and do some other work. Let this thing do some of the lifting on here. And so here you're going to see, again, this is not sped up. This is not slowed down. Just want to qualify, these are engineering development boards. They're not optimized. We're not running at final clocks. We still got work to do here, not final software. But I wanted to give you an idea, even at this very early stage, hopefully my laptop is going to not introduce a lot of overhead, but to see what happens. And you can see it starts to think, and it's going to give you a response. Again, we should have had some dramatic music playing for this. Got to get some production values next time. Need budget. And I think it's about done. So you're all some of the first people outside of NVIDIA to actually see a Spark system actually take a model, train it, and run it and give you a query. So that's it. You actually saw it live. So you're the first people on the planet to actually see it outside the lab. So just recap what we saw. I know we looked at a lot there. There's a lot of words, a lot of things on the screen. It might have been hard to see from where you're sitting. But, fine-tuning is definitely computationally a heavy load. You need a lot of memory. You need a lot of flops. There's a lot of data. And that's where the TOPS performance and the memory comes in. And our stack has already been ported to ARM64, so a lot of the tools and things we use in our DGX just work. So if you're in a DGX environment, everything just kind of works there. We've got all support for all the dev kits. You saw us running lots of things. We're running quite a few different pieces of code. I always forget everything that's going on there, but I wrote some notes. I was smart. We were using Hugging Face TRL. We used Bits and Bytes for some of the translation stuff. PyTorch, CUDA was there. Jupyter was the notebook we used there. So all, again, third-party tools that run in the environment. It wasn't just a straight NVIDIA stack. Of course, we had all of our CUDA optimized tools there, CUDA X tools running. So it's really, you really can't overstate the importance of the NVIDIA ecosystem, right? That is just a huge advantage when you're doing AI work, and we want to make sure that all runs on Spark and that it makes it for you to be able to seamlessly move through these different workflows. And so, if you look at some of the advantages when we talk about this being for developers, this is really it, right? You can run large models, large workloads right there on your desktop. We've got the NVIDIA software stack. It's got the tools you need to build and run AI. Very important to remember, the data stays local, right? We didn't have to take any of our source code, anything out of the building, right? It stayed there on the rack in the environment we put it in. Very important if you've got private data. I know some people who tell me they spend time creating synthetic data because the real data they want to run on can't leave the building. It takes time, right? It takes effort. You can skip that step. Keep it local. It's your own personal AI cloud. You don't have to fight for contention. You don't have to beg for time on the clusters. You have to go get more money for cloud resources, right? It runs there. It's yours. If you want to change the software, you can do it. How many have tried to change software in a cluster before? How many have been successful, right? It's hard to do, right? They really protect those systems and those resources. So this is your box. You can do with it as you will. And you can connect two of these together to really go up and expand into some workloads. So, as Jensen mentioned, these are really part of a new class of computers created for AI. People ask me, oh, can I use it for this? Can you do that? It's really an AI box. If you've got a laptop, and you want to do something like we did the training, I see Kadar's here. If you had to lock up your laptop for 5-6 hours during the training run, that's a lot of time. You're not in meetings, you're not reading your email, you're not doing all the other stuff you got to do, right? So it's a heavy lift. So this is a great way to offload your desktop systems and not have to go to some of those other resources. Software makes it easy to migrate to DGX Cloud, any of our accelerated infrastructures. It's going to be available from OEM partners. We showed the ones up front from Asus, Dell, HP, Lenovo. So if you've got a particular favorite vendor you like to buy from, you'll be able to get it from them. You can go check out the models. Asus, Dell, HP have their versions of this in their booth. You can go get a picture and go get a selfie with it probably if you ask nicely. And you can reserve your system. So you can go to NVIDIA, the marketplace, and NVIDIA.com, and you can reserve a system. Think of these gold systems as founders editions, right? We're going to make some of them and sell them, but it's going to be like a founders edition. Once they're gone, they're going to be gone. And we really want our partners to go out and sell these, and that's where the volume and the mass production is going to come from. So if you want to get a cool one, I reserve one. You want one that's just like this and looks cool and sits on your shelf, then get a gold one. But you'll be able to get them. This is a 4 gigabyte storage option that we have available there, so it is $39.99. You can save a little money and get a 1 terabyte option. They're going to be cheaper. I know we announced that at $29.99 at CES early in the year. So it just depends what you want to do. There's plenty of USB-C ports on there, so you can plug more storage into it if you like and save yourself a little money. I might reserve yours today. And so with that, I think we'll just turn over to questions. Yeah, go ahead to the mic, and I'll have some more box water while you go there.
Thank you for the presentation. So some quick questions about the hardware. How hot does it get? How much power does it require? And can we change the drive inside?
Sure, good question. So 3 questions there. One is how much power, how hot does it get, and can we change the drive? How hot it gets, I don't know yet. It should be cool. It's going to have a fan, and it's a very small, low power device. Power, we won't know final power budgets until we get the systems in-house. They've got to lock the clocks on CPUs and GPUs and everything, and that will determine power. It's going to easily plug into a wall outlet, still think 200-ish watts, give or take, but we still got a little testing to do before we have that. And it's not really intended for you to go in there and use it, change the drives or any of the components in there. So it's not going to be something where you can easily go in and swap things out. We're not really building that kind of system. It's kind of meant to be a little all-in-one and kind of built that way. Now, what our partners do, I can't comment. So you can go and ask Dell and HP and Lenovo if they have plans, and maybe they have something different than ours.
To build on the power question, so are you planning on having a separate power brick for the 200 watts then? Because I think the pictures of the prototypes didn't show a power plug.
Yeah, there's no power plug. It'll plug in through one of the USB ports, and it's going to be an external power brick to help keep the size down. And it makes it easier for multiple countries. That way it's kind of hard to do it internally and be able to ship globally that way.
Okay, so you're going to be limited by the power profile that USB PD can provide then, right? Mm-hmm. Okay. The other question is, since NVIDIA is also a switch company, have you thought of having like a companion switch that has, say, an NVMe storage, so that I can truly simulate like the cluster environment where I have object storage, through the switch provider, and I can hook up like these like maybe 2 or 3 of them together through this, whatever. I presume it's 100 gig is what you're doing.
It's a 200 gig on the switch, on the output there for the
yeah. So like have a little like NAS type device that goes with this, with your cutesy branding, right? Yeah. But have the storage available with it, provide an object storage, and I guess for extra fun and bonus points, right, have a way for me to put like a Slurm controller or login node on it, and then I have my mini cluster, all in a nice little stack.
Yeah, so we've had some discussions about, do we make a switch for these, a ConnectX switch? I think in most cases it's probably way more expensive than the box is for a switch. So, but for now, we're just going to go let you connect the 2 together. I can't speak for what our partners want to do longer term and how they want to support it, but that's kind of our plans. But again, this is like a founder's edition, so we don't we're really not in the system business, so we don't build systems, so we don't intend to do that. But our partners may do. Again, I would stop by if that's something you like. I would go stop by Dell and HP and Asus.
That'll also just be a standard DAC cable for cross
Yeah,
connect.
it's a standard cable. If you go look, you can see there's one plugged into the back of one of the little stack in the booth downstairs.
Thanks.
I had a question about memory bandwidth on if you can tell us anything about it. Just like
Yeah, there's actually, I think I had one more slide here, but
I'm mostly curious about how it compares to a GPU, and because it's memory
it's
bandwidth
much less. So there, take a picture of that.
Cool.
But the memory bandwidth is up there. It's 273 gigabytes per second.
Because like in my experience, it's really important for like inference speed for the the size of the model.
Yeah.
So I was wondering. Did you guys do like a bunch of optimization on the software side of things to make it run much faster on?
Yeah, we're always looking at optimizations and things and we showed that chart is if it fits in memory, it's going to be faster on a discrete GPU. You've got more flops, you get more memory bandwidth. That's just the way it's going to be. The sacrifice you're making here, we give you a lot more memory in a very tiny footprint little device. And you can see it's using the memory on there is LPDDR5X, so power efficient. It's more like
So it's not
laptop
like
memory.
GDR7 where you get like 2 terabytes. Yeah,
And you need a lot more power. We could not make something that's that power efficient with that kind of memory. It's just
I wish.
Yeah, we can only hope. But today we're not there.
Okay, cool. Thank you.
And we've got the specs live on the webpage. The webpage's been refreshed, and so all these are up there. So if you didn't get a picture, you can go check out the webpage, and we've got all the specs up there for the system. Yeah.
Maybe I missed the details. So how do you connect the two Sparks together?
You connect them on the back. I'll get the little modeling. I like carrying
What's the
model,
bandwidth
so.
between those connect?
Kind of like Wheel of Fortune. There's 2 large connectors on the back that connect to the Connect
Is it
X switch. And so you would plug one of these into.
Right. What kind of connector is it? Is
It's
it NVIDIA?
It's a Connect X7. It's a fairly large connector.
Okay. Is it InfiniBand or
It's not InfiniBand. No,
Ethernet? Okay.
it's a nice, good old-fashioned copper cable.
Hi, great stuff. When are you going to ship them?
That's the $64 question. We're saying they'll be shipping this summer, early in the summer. So if you go on and reserve it, hopefully you can have some time by the pool this summer and enjoy your Spark. It should be available.
All right,
So,
thanks.
our partners have their own schedules, so they'll provide those later. That it? Got time for one more, I think. I'm looking at the red clock there, and I'm going to get flagged in a minute, but we have one more.
I have a question about the storage. In terms of storage, like you guys are using 1 or 4 terabytes NVMe M.2 SSD drive, and do you have any preference on PCI generation for that?
It's all NVMe M2. I don't know what the generation. What is it? 5? We're at 5. So PCIe 5, Gen 5.
Oh, PCI Gen 5. Okay.
Can we get one more in?
All right, you got 2 minutes left. You've got probably a minute and a half by the time you get up there.
So what kind of clock speeds are you targeting and what kind of GPU am I getting? I only see Blackwell generation up there. How many cores do I get? And
Yeah, we'll provide some more data. Until we lock those down, I don't know what the clocks are going to be, the final clocks, until we get the boards back. They do a lot of testing and validation, and then they'll lock them down, and then we'll have the core counts and everything. And we'll provide those for you.
But I guess core counts are locked in by now.
More or less, yeah. We haven't shared the core counts yet, but we will soon. Right.
Outstanding. Okay, thank you so much for coming, everybody. This brings us to the end. Enjoy the